In today's session, I'm going to teach you the concept of linear regression. Uh, Before starting, I will tell you that I'm going to take three PDFs here. So I'm going to take two notes. One is this one, and the other one is this one, based on linear regression only, and then a handmade notes. Okay. So I'm going to teach you from these three PDFs. So it will help you to make the concept very clear and you can be able to understand it a lot better. So let me start with the this linear regression part. So before starting that, let's see what is the building machine learning models. So building up of machine learning models. Okay. So the main goal is to find an equation of distribution that fits the data set. Okay. So there are various machine learning models available, and for every use case, different models are used. So let us understand some of the famous and commonly used machine learning. So here are the machine learning models that we are going to see in the coming sessions. First, I'm going to teach you the linear regression. So let's start with the linear regression part. So linear regression, it is a type of supervised machine learning model. It is used to perform regression tasks. Regression models a target prediction value based on independent variable. It is mostly used for finding out the relationship between variables and forecasts. So linear regression is nothing but it is you are actually finding the dependent variable regression line. So you are drawing a regression line in such a way that most of the data points are covered and most of the data points are within the above or below the linear regression. So okay. So so here we will consider independent variables, okay, and how the independent variables are defining the dependent variable. So we will see that. So if you see the sales of TV when the advertisement was done, you could see that the sales is really high when the TV's advertisements are higher. Okay, so these are the data points. Okay, this is like a linearly you can draw a linear line from this. Okay, so this is independent variables x and this is the dependent variable y. So this is like the equation of line, right? So this is the equation of line where you have a slope m and this will cut somewhere over here and that is slope and intercept. Okay, intercept is somewhere over here. So linear regression makes prediction for continuous or numeric variables such as sales, salary, age, product price, or etc. Okay. And regression algorithm shows a linear relationship between dependent and one or more independent variables. Okay. So there can be a dependency of more than one independent variable for the dependent variable y. Okay. Hence, this is called a linear regression. This linear regression shows the linear relationship, which means it finds how the value of dependent variable is changing according to the value of independent variable. So this is what I told you, right? So we will see how the dependent variable is getting affected by the independent variable. So we'll see that. And we will have multiple variables, independent variables. We'll see how those independent variables are actually affecting our dependent variable. So so let me go to the next linear regression part and see some other concepts before dealing with the algorithms for linear regression. Okay. So, so linear regression is a linear model. Okay. As I said, this is a machine learning model, right? So it's a linear model. Example, a model that assumes a linear relationship between input variable and a single output variable. This is just a model that has a relationship between input variables and one output variable. More specifically, that y can be calculated as a linear combination for input variables. Okay. So y is nothing but the output, and output is nothing but the relation is the combination of multiple or the input variables x. Okay. So linear regression model representation. The model for a simple linear regression would be y is equal to b naught plus v1. If you see this, this is kind of a y is equal to mx plus c relationship, right? This is an equation of line where mx is like this is a slope b1 and B naught is our constant. Okay. So B1 is like B1 and B naught are like coefficients. Okay? So we have to find the coefficients of B1. We have to find coefficients B naught and B1. This is that we are going to discuss in this linear regression part. How the so we will be given values Y and values X. So we have to find out B naught and B1. And using this B naught and B1, whatever input you will get, we will find the y part. Okay, so that is what we are going to determine. So when we have more than one input in higher dimension, the line is called a plane. Okay, or a hyperplane. So this is in higher dimension, more than one input. The form of a equation and the precise numbers utilized for the coefficients are hence the representation. Example, b naught and b1 in the example. Okay, these are the coefficients. Okay, coefficients of x. And this is the constant. It is usual to discuss the complexity of a regression model, such as linear regression. Okay? The number of coefficients employed in the model is denoted by this. This is how it is denoted. When a coefficient reaches zero, it effectively removes the influence of the input variable. Obviously, right? If this becomes zero, then the influence of the input variable will be removed on the model. And as a result, the model prediction will be 0 into x. Okay? So this is important when considering regularization strategies, which alter the learning algorithm to minimize the complexity of regression models by exerting pressures on the absolute magnitude of the coefficient, driving sum to 0. So this is what happens. Like if you have a output, and if you're constant that the coefficient becomes zero, then x will have no influence, right? So this is the problem. This is not possible. Okay, in our case, linear regression, well, it's zero slope. That is not going to happen because that will take out the influence of x. Okay. Now that we have covered the representation used for a linear regression model, let's look at several models for learning this representation from the data. Okay. This is so before coming to the linear regression, learning the model part, now let me cover the notes that I have written. So just understand this thing that I'm going to discuss. Okay. So what is linear regression? It's a technique to model the relationship between two types of variable by fitting a linear equation. Okay. What is that? It's a technique to model the representation between two variables, two types of variable, by fitting the linear equation. So just you have to understand, model the relationship and linear equation. Okay. So it's modeling the relationship between two variables, types of variable, that is input and output variable, by fitting a modular equation. So it means we are fitting a linear equation in such a way that we have a more relationship between input and output. So we have seen that in the previous statistic class, variance is of one variable, that is univariate, right? Variance is a univariate analysis, so it deals with one variable. But covariance is a two variable, right? So two variable and it gives them direction. We have seen that in the previous statistic class. Covariance is of two variables and it gives two direction, whereas correlation is also of two variables but it gives direction as well as the strength. Strength is nothing but the magnitude. Okay. So, and you have seen that magnitude can lie between -1 and 1. So, how, if it is -1, the correlation, then it is strongly negatively correlated. That is, the increase in x is equal to decrease in y, and it is strongly correlated. And +1 means it is also strongly correlated. +1. Zero is weakly correlated. That is, there is no relationship between X and Y. Like that kind of concept is correlation. So coming to regression, so regression is like direction, it gives trend, as well as how change in one variable attributes to change in other variable. Okay, so this is like how change in X will affect the change in Y. So from historical data, we have found out that the price of houses depend on its size, right? So we have seen this kind of data. Okay, so let's say P price is directly proportional to. So let's say P is equal to k into 6. So let's say the size of a house is 1,000 square feet and its price is 80 lakh. Okay. For 1,000 square feet, if the price is 80 lakh, so if you want to know what is the price for 2,000 square feet, you have to find the constant over here, right? So you'll find the constant P is equal to K into size, and K comes out to be 80 lakh by 1,000, which comes out to be 8,000. Okay. So K is our 8,000. So for a house with 2,000 square feet, we'll have 2,000 into 8,000. Okay. 2,000 square feet into 8,000, which comes to be 1.6 crore. Okay. So this is how it is. So now let's take a linear equation of a line, which is y equal to mx plus c, where m is the slope and c is our intercept. In this chapter, we'll say m is a c is m and c are coefficients, that is we are going to find, and c's are obviously the intercept and constant. Now we have to find slope and c, that I'm going to discuss. Okay. So if you take this, so we have point P1 and point P2. Okay. So let's say the point P1 has a slope M1, and so the equation of this line become y is equal to M1 x1 plus C1. Y, and this P2 becomes y is equal to M2 x plus 2 plus C2. Okay. But you know that the intercept is same, right? So instead of plus C1 plus C2, we'll write C, because the intercept is over here for both the slopes. So, right? So we have point P1 and point 2, V2, we are passing the data. So equation of line is here is y is equal to M1 x plus C1, y plus y is equal to plus M2 x2 plus C2 plus that is C plus C. Okay, since it's a intercept is only 1 point over here for both the line. So using mathematics, so what happens is that in regression line, so let's say, let me take this example. Okay, so we have so many data points, right? First we will draw multiple lines over here. Okay, we draw multiple lines and we will see the best fit line which covers most of the data points and which gives the very very less error. Okay, which gives very less error. Okay, error is nothing but the cost function over here. We are trying to find out the cost function which is having very minimal value. Okay, so in our case, so coming to this problem, let's say we have multiple lines and we got the best fit line to be this. Okay, so if I have to show you in the below part, I have got, so let's say, so these are the multiple lines, and we will find the best fit line. Okay, so let me teach you this concept. Wait a second. So let me come to this. Okay, so we'll draw the best fit line. So from the multiple lines, we will take the best fit line. So error is distance between predicted and actual. So let's say this is our line, and these are the data points here, 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 and here. So data points are present over here. So now you have to find out the errors. Okay. So error is nothing but the actual value minus the predicted value. So this is the predicted value. This is the regression line, and what is the actual value? So error comes out to be y actual minus y predicted. Okay, y actual minus y predicted here comes out to be 1.5, and here y actual minus y predicted comes out to be 5, and here it comes out to be 3, and here it comes out to be 2.5. So in the negative region, y actual minus y predicted comes out to be 2.5. So you have to understand that whenever you are trying to find the error, it should be always the absolute error, because otherwise the upward point and downward point get cancelled out. Like y actual is lesser than y predicted, right over here. You can see y actual is lesser than y predicted. So we are considering the absolute value. So that's one. So if you see that here, so we have one, okay, error of one, p actual minus p predicted from here to here is one, and from here to here is one, 1 plus 1 plus minus 0.5, right? So y actually is less than I predicted. So I will take the absolute value as I said. So plus 1.5, plus 5, plus 3, plus 2. Okay. So error comes out to be 14. Always understand when you are finding the error, you have to add, I mean, you have to take the absolute value of y actual minus y predicted. Otherwise, the positive and negative error gets cancelled out. Our aim is to find the best fit line, which is having error as minimum. Okay. So the equation of line, we have y is equal to mx plus c, where m is the slope and y is the c is the intercept. This is our independent variable x. Okay. Our goal is to find statistically significant values of slope and intercept that minimizes the error. Okay. So let's say y predicted is 65 and y is 68. So what is the error? 3. Y predicted is 60 by a 60. That is the error. Y minus y predicted. That is 10. What is the y predicted? Y minus y predicted for this case? That is minus 10. You have to take absolute value, right? So 3 absolute is 3, 0 absolute is 0, and minus 10 absolute is minus 10. So that is 10 positive. So error is nothing but, in this case, we are considering error as a residue. Okay. So that is y minus y predicted. Okay. So ways to think about the error. Okay. So we can take error to be absolute, or we can take it to be squared. You know why we don't take absolute in errors? Because what happens is that here we are trying to find the minimum. Okay? When you are trying to find the minima, the differentiation of absolute becomes zero. That is, you know that d by dx of absolute, that is error, y minus y cap becomes zero. So we are not trying to use absolute value in our case. We'll take the square. That is, square means we are taking the sum of square residual. Okay, whatever absolute value you're getting, you square it. Okay, you square 3 square plus 10 square, like that. Okay, so you're taking the y minus y cap whole square and you're still summing it all the squares, square residuals. Okay, so that is called error, sum of square residuals. You can see that absolute value cannot be cancelled because the differentiation of this will become zero. Okay, but when you square this, you will get minima. Okay, when you differentiate this, the differentiation of constant becomes zero for absolute, but this is not zero. Okay, this is differentiable. Okay, so now let's see the algorithm. Okay, so we have seen this sum of square root. So let me come to this. So algorithms for linear regression. We have ordinary least square, we have gradient descent, and we have simple linear regression. Let's come to ordinary least square. When there are multiple lines, we can utilize ordinary least square to estimate the coefficients. Here the coefficients are B naught and B1. Okay, the B naught and B1 are our coefficients. We have to estimate the coefficients. Let me read it once again. When there are multiple inputs, we can utilize ordinary square to estimate the coefficient values. Why we want to estimate the coefficient values? So that we'll be able to do the prediction for the input, whatever input we get. Okay. There can be multiple lines that can be used to represent the set of data values. So you can see that this is how the data is distributed. And if you draw the linear regression line for this, there can be multiple lines that crosses. Okay, from here to here, it will cover data points. From here to here, it will cover data points. From here to here, it will cover, and from here to here. But how to decide which is the best line? See, you have to note this. The line with the maximum points around it seems to be the best fit. So which is the line with the maximum points around it? So if you take this point, you see 3 points are covered, 6, 8 points are covered. And above there are 3 and below there are 6. So this is like somewhat covering the maximum lines, right? So green one looks the best from this figure. The closest the points are to the line, the better is the fit of the line. Is the line. So this is the closest point to this line, right? These points are closest to this, and these points are closest to this. So the goal is closest the points are to the line, the better fit is that line. This implies the distance of the points from that line is important. Okay, the distance from the point of the line. So if you take this regression line, so if you take the value x over here, and for value x, we have a predicted value, the actual value is here, and our prediction value comes up in here. So this is the difference between the predicted minus actual. This is the error, okay? So now if let's just consider this is the predicted. Now let me see you. This implies the distance of the points from that line is important. The line with the maximum points around it seems to be the best fit, okay? So let's take the point over here, okay? So you can see our data is over here and our actual value is over here. You can take this difference, okay? And data is over here, actual value is over here, but the regression line shows the value over here. I mean, let's take this point, okay? Let's take this point. The regression rise is over here, y predicted is over here, but y actual is okay. This is the error, okay? The difference between actual minus predicted is our error. And I'm going to teach you small concept related to that. So suppose at point x, the value y is denoted by y actual. Let's take a point x. The value y is denoted by y actual. This is y actual. Okay, so you can see the point here, right? Now the corresponding value on the line is denoted by y predicted. This is our y predicted. The difference in these two y values is called the error or residual. This is the difference between y actual minus y predicted is the error. Residual is y actual minus y predicted. Since some points are above the line, so the residual would be positive, and some points are below the line, so the residual would be negative. Obviously, if you subtract this minus this, you will get negative, and if you subtract this minus this, you will get positive. So the residual would be given. Hence, when the total residual is calculated, it does not give the true picture of due to negative sign. Yeah, okay. When you find the total residual, this and this will cancel out, and minus point minus values and plus values will cancel out. So what should we do in that case? There are two ways to remove this negative sign. Find the absolute value of the residual. That is what I said over here. Find the absolute value of the residual, or you can find the square of each residual. When you find the square of each residual, you will get a positive sign. Okay. So the concept underlying the linear regression model is to obtain a line that has the sum of squares of deviation. That is, the sum of square of the sum of square of deviation is ordinary least square. That is how it got the name ordinary least square, because least sum of square deviation. So you want to minimize the residual, then you have to summation. So you have to minimize the residual. So you have to find the value of intercept and the slope in such a way that the cost function or the error is minimum. Okay. So this is the sum of square residual y actual minus y predicted whole square. So before coming to gradient descent, let me teach you this over here. So linear regression, learning a linear regression model entails estimating the values of the coefficients used in the representation using the given data. In this section, we will take a quick look at four methods for creating a linear regression model. This isn't enough knowledge to build them from scratch, but it will give you a sense of computation and chaos. So let's come to simple linear regression. When we have a single input for a basic linear regression, we can use statistics to estimate coefficients. Okay. The necessity is calculating statistical features such as mean, standard deviation, correlations, and covariance from the data. To traverse to calculate statistics, all of the data must be available. So leave this simple linear regression method for now. Let's consider the ordinary least square that we just discussed from the previous PDF. Okay, when there are multiple inputs, we can utilize ordinary least square to estimate the coefficient values. Okay, so when there are multiple inputs, we can utilize ordinary least square to estimate the coefficient values, that is B naught and B1. The ordinary least square approach aims to reduce the sum of square residues. That's what I said. Okay, we have to reduce the sum of square residuals, that is the cost function. This means that given a linear regression line across the data, we calculate the distance between each data point and the regression line. Okay, square it and add all of the squared errors together. Ordinary least squares aim to reduce this sum. This is what ordinary least square is doing. So find the error by actual minus by predicted and square it and submit over all data points, that whatever you got. Okay, square it and add all the sum squared errors together. That is the error. Okay, ordinary least square aims to reduce this amount. So we want to reduce this amount. Okay, so we want to reduce in such a way that the linear regression line, whatever you are drawing, it should give error minimal. Okay, should it should at least cover almost all the data points. This method analyzes the data as matrix and employs linear algebra. You know, right? Y is equal to mx plus c is like a matrix. We can represent in the form of matrix, and this is an algebraic operation to estimate the optimal coefficient values. That is m and c. It implies that all of the data must be, pardon, let me repeat to you once again. This method analyzes the data as a matrix and employs linear algebraic operation to estimate the optimal coefficient values. So we'll draw it in the form of matrix and we'll find out the coefficient of x and as well as the constant c. It implies that all the data must be available as well as sufficient memory to fit the data and perform matrix operation. So we need all the data to be available so that we can draw the linear regression, that is the regression line, in such a way that it can cover all the data points that are present. It is unusual to implement the ordinary least square algorithm yourself unless as a linear algebra homework. You are more likely to use a procedure from a linear algebra library. This process is extremely fast. Okay? So let's see the notes part that we have seen. So I have already told you we have actually kind of calculating the sum of square residual. Okay. So for error, we find sum of square residual, that is y actual minus y predicted whole square, and then submit all the errors part to find the sum of square residual. So we have two algorithms to find in the regression line. So we use ordinary least square, finding the best fit line, and we have gradient descent, which is a step by step. So how to become great? Either you can keep getting better or keep minimizing error. Okay, there are two ways, and let's see ordinary least square here. So ordinary least square is nothing but covariance of x comma y by variance of x. That is variance of y with respect to x divided by y variance of x with respect to x. This is what it tells, okay? So when you do apply the formula of variance of y with respect to x and x with respect to x, the n minus 1 denominator part gets cancelled and you will get summation of x minus x bar, that is mean, actual data point minus mean, and y minus y bar by x minus x bar whole square. So you don't have to worry about this part more. Let's come to the gradient descent part. Gradient descent is one of the important concept topics you need to understand, which is going to be used a lot while solving the linear regression problems. Okay. So the gradient descent Let's imagine a person who is coming down the mountain gradually and reached the valley which is placed at the bottom of the mountain. Okay. So what will happen? The person is automatically taking large steps when the slope is steep and takes smaller steps when the slope is very steep. Hence, till he reaches to the village, the person decides his next step based on the current position. Okay. It is an optimization algorithm and it works stepwise. Okay, gradient descent is an optimization algorithm and it works stepwise. Optimization in the sense it will check again and again and it will find the best fit slope and intercept where our const function is minimum. The aim is to decrease the error stepwise. Okay, we have to decrease the error stepwise. In this algorithm, the error is considered as cost function. Okay, the error is nothing but a cost function in this algorithm. Hence, minimizing the cost function is the final goal. The loss in the error in our predicted values of W and B. Okay, the loss is the error in our predicted value of W and B. So error is also denoted by sum of square residuals. So sum of square residuals is y minus y actual minus y predicted whole square. Here y is y actual, yi is y predicted, and yi is ywx plus b. That is yi is the predicted, right? This is the yi is a equation of a line. Okay, this is the yi is a regression line. Okay, this is yi. And what is yi? Wx plus b, where w is a slope and b is the intercept. Okay. Therefore, h of phi. So let's call this h of phi, which is our const function, is summation of y minus wx plus b whole square. Okay. To find the minima, differentiate the equation with respect to slope and then with respect to the constant value. So we have to find the minima, right? I mean, we have to find this. Okay. We have to find this minima where our slope or equation of line with respect to slope, we have to differentiate the equation of line with respect to slope. Then we have to respect to constant we have to find. Okay. So this is the minimum where we have to find the cost function reaches zero. We have to make sure that the cost function at least reaches zero. A cost function of zero indicates that 100% accuracy. So we are trying to minimize the cost function, which is our error. Okay. For that to happen, we have to find our slope. Okay. So we have to find our slope. We have to reach this position. Okay. We have to reach the position. And once we reach this position, we'll get our slope and intercept. That is d by dx minima. What is the minima? Dy by dx is equal to 0, right? So we'll get the dy by dx as 0. Okay. So differentiate with respect to x, okay, or w. Okay. First, we have to differentiate with respect to w, which is our coefficient of x, and then we have to differentiate with respect to constant, that is b. Okay. We are doing this because we have to find slope and intercept as we will be having the x and y. So we have to find slope and intercept. Okay, we will have x as well as y. If we want to predict y for the given value of x, then we need slope, right? Slope and intercept. Then only we can calculate the value of y. So for that, what we will do, differentiate with respect to w. We have to differentiate with this equation with respect to w. Let me show this in this form. So gradient descent aim is to minimize the error, that is the cost function. Sum of square residual is y minus y gap. Y gap is our predicted value. So cost function is h of theta, summation of y minus wx plus b. Y predicted is the equation of line. So it's whole square y minus wx minus b. When you differentiate with respect to W, we get this as dW, all this as dW. We will get 2 into y minus wx minus b into minus the x. Okay, we are differentiate with respect to the dW, right? W. So we'll get the value x over here, coefficient of W, which is x. It is negative, right? So minus x. So minus 2x into y minus wx minus b. Check this. Minus 2x into y minus wx minus b. So now we will differentiate with respect to b. It's not given over here. Let's say, yeah, it's given over here. So when you differentiate with respect to b, b, there is no coefficient of b. So 2 into y minus wx minus b into this coefficient of b is only 1. So minus 1. Coefficient of b is minus 1. So minus 1 will come. So minus 2 into y minus wx minus b. This is of the equation like 2x of y minus wx minus b, wx plus b is y cap. So minus of wx plus b is y cap. That is y cap is like y predicted. Minus 2x into y minus y predicted. And this db comes out to be the 2 into y minus y cap. So now what we will do, you see, differentiate with respect to b. So the next w value in the slope is given by w next is w minus alpha dw. So here is the slope, right? The slope is changing. You could see, right? The slope, initial position of the person, and this is the slope, and now it changes, and now it changes. So, okay. So what happens is the next value of slope, next value of the slope will be given by W next is W minus alpha into dW. Okay. W next is current value of W minus alpha, which is the learning rate ratio. Alpha is the learning ratio, and dW, which is we have differentiated with respect to dW. Change in W. So I will repeat once. The next W will be the next slope value will be the current slope value minus the learning ratio minus the learning ratio into differentiation of dW, differential of the current slope value. So slope value equation. So now what you will get is that learning rate is value that helps decide the next slope. Okay, this is actually helping us to decide what is the next slope. Okay, what is the next slope? The alpha is going to decide. The curve of the cost function is a U curve. We have seen that this is a U curve, and the curve of the cost function is a U curve. So learning rate helps us to decide the right amount of jump from the previous slope to the next slope such that minima is reached. So learning rate helps us to decide the slope from the previous position to next position so that minima is reached. Okay, next slope so that minima is. A large value of learning rate may result in missing the minima. What happens is that if you give a large value of learning rate, then it might jump from here to here and then it might jump from here to here, right? So what will happen then? It will, if jump from here to here, then we will miss the minima point. So the value of the learning rate may result in missing the minima, whereas the small value of learning rate lead to increase in the number of steps. Okay, this is the what happened. So the learning rate decides the right amount of jump from the previous slope to the next slope such that minima is reached. A large value of learning rate may result in the missing the minima, whereas the very small value of learning rate may lead to increase in the number of steps. Okay. So very small value of learning rate means the small steps it will take here to here, here to here, here to here, here to here, here to here. So it will take some time to reach the minima point. Okay. But it will give the accurate result, and but it is too complex also and maybe become too complex, but it will give accurate result. The next b value in the given slope, so next b value, so what wherever the intercept happens, okay, here, so here intercept wherever it happens, it also gives the intercept. The next b value slope is given by b next is w. Actually, this is B next is B, okay? This is not W, okay? This is by mistake they have considered B minus alpha into DB. Let me show you that. W next is W minus. So this is how it happens. Small steps it will take based on the learning rate. Let's say our current value of slope is 5, then minus 0.1 is our slope, and dw when you differentiate and get the value, it comes out to be minus 0.25. Okay, minus is there, so 0.25 it comes out from this equation. So plus, so slope will increase. Okay, and similarly, the b next is b minus alpha into db. This is learning rate. Okay, b minus alpha into db. Steps we need to follow to find the gradient descent. Initially, let W is equal to 0 and B is equal to 0, or you can take W is equal to 1 and B is equal to 1 as well. Okay. Let L be our learning rate. Okay. This controls how much the value of M changes with each step. L could be small as 0.1 for good accuracy. Calculate the partial derivative of loss function with respect to x, with respect to w. Okay, that's done. And plug in the current value of x, y, w, and b to obtain the derivative of h of phi. Okay. Now what happens is that calculate the partial derivative of the loss function with respect to w. So we have done that. And plug in the current values of x, y, w, and b. So apply whatever values you have, x, y, w, b over here into the obtain the derived value of h of x. So you will get the value from that. After applying that, now we update the current value of w and b using the w next and b next. So now apply dw value over here. Whatever you got, this is dw, right? Whatever value you got, you apply over here. You have current w value and you have alpha as the learning rate 0.1 and apply dw. And similarly, you'll have b next is current b value. This is b, okay? This should be b minus alpha learning rate and db, the differential of constant. We repeat this process until our loss function is a very small value or ideally zero. Okay. Our loss function is what? This. This should be ideally zero, which means zero error or 100% accuracy. The value of W and B that we have left with now will be the optimum values. When this becomes zero, then whatever values of W and B you got after doing the operations and all, that will be your optimum value, and that can be used to find the output y or input x. Okay, so let's say you have an input x over here, and for that you have to predict the y variable. So you have a slope, then we have an equation of line y is equal to mx plus c, or y is equal to wx plus p. You have w, you have x given, and you have the intercept. Apply that and you will be able to find the y value. Yes, so this is all about the gradient descent part. So let's see what's there for gradient descent over here. So gradient descent, when there are one or more inputs, you can employ a procedure of optimizing the coefficient values by iteratively minimizing the model's error on the training data. So we are optimizing the coefficients by minimizing the error of the training data. That's what we did. Model's error, okay, on the training data. Gradient descent is the name given to the operation which begins with random values for each coefficient. So we will take some random values for each coefficient, that is w and b, which is a slope and intercept. That is, we will take usually 1 and 1, slope and intercept, or you can take 0 and 0 as mentioned over here. But I would prefer to take 1 and 1. For each pair of input and output variables, the sum of squared errors is computed. Okay. Sum of square errors will be computed for each pair of input and output values. Pair of input and value, the sum of squared errors is calculated. Sum of square errors is the residue. Okay. Sorry guys, I had a network issue. So let me repeat once again. So gradient descent is the name given to the operation which begins with random values for each coefficient. Okay. Some random value will be given for slope and intercept. For each pair of input and output values, the sum of squared error is computed. Okay. For each pair of input values and output values, there's a sum of square error is computed. As scale factor, a learning rate is used. We have seen that. And the coefficients are updated in the direction of error minimization. We have also seen that. Okay. So I will be writing a code for gradient descent. We'll understand that clearly. Okay. The technique is repeated until either a minimum sum squared error is obtained or no further improvement is achievable. Okay. Either we will get minimum value of the cost function or there is no improvement is achievable. They will find that till that point. When employing this method, you must choose a learning rate parameter that sets the magnitude of the improvement step to take on each procedure ability. repetition. Okay, for this method, you must choose a learning rate. That is alpha is we have taken 0.1. So that sets magnitude of the improvement step to take each procedure. Okay. So gradient descent is frequently taught using linear regression model since it is a simple to understand. In practice, it is handy when you have large data set, either in terms of number of rows and columns that may not fit into the memory. Okay, so now let's come to this linear regression part that we have done. Okay, this is done, right? So this is also done, making prediction with linear regression. Again, let's see this. Should we see this? Okay. So let's see this. Okay. So making prediction with linear regression. Making a prediction is as simple as solving the equation for a certain set of inputs, given that the representation is a linear equation. Okay. And let me illustrate this with an example. Assume we are predicting weight y based on height. For this situation, a linear regression model will be y is equal to b naught plus b1 or x1. That is, weight is b naught plus b1 to height, where b naught is the bias coefficient and b1 is the height column coefficient. To obtain the descent set of coefficient values, we employ learning rate technique. Once discovered, we can anticipate the weight by public plugging the different height values. As an example, let's consider B naught intercept to be 0.1 and B1 that is a slope to be 0.5. Let's enter them in the given weight of a person who is 182 centimeters tall. So we have to find the weight. So we have calculated the B naught and B1 as 0.1 and 0.5. So when you calculate that, you will understand that the weight comes out to be 91.1 kilogram. As you can see, the above equation can be displayed as a two-dimensional line regardless of our weight. The B naught is our strong point. We can go through a series of heights ranging from 100 to 250, plug them into equation and get weight values to create our line. This is how weight varies. This is how the equation of line is for computation of weight based on height. Okay. So this is our intercept point and this is our slope. We can find out, take from here for this point to this point, from this point to this point, and just find the slope. So this is the regression line that we have drawn, and our data points will be distributed around this line over here, and different depending on the data that is given. Okay, depending on the trained data set. So let me start writing a code for gradient descent so that you will be able to understand it on a more clear note. So let me start writing code. First, we will import NumPy. So import NumPy library. So you know that NumPy is used for numerical Python. That is operations related to array. So let me pass x array to be np dot array of 1, comma 2, comma 3, comma 4, comma 5. Okay. Let me pass the output for this as np dot array of output comes out to be 5, comma 6, comma 7, comma 11, comma 13. Okay. So this is just like a the training data that we have. This is not the training data. This here we are just trying to compute the slope and intercept based on these values. Okay. We are getting for one, we are getting 5, and for 2, we are getting 6, and we are for 3, we are getting 7, right? There is some kind of equation that is present for this. Okay. So we have some kind of equation y where y is mx plus c kind of equation. We have x, we have y, we have to compute m and c. So for that, let me define a function called gradient descent. And let me pass this x and y over here, x and y array. Okay. So for easy computation purpose, I will take slope as 1 and intercept as 1 as well. And as I said, learning rate is 0.1. Okay. 0.01, sorry, okay, 0.01 learning rate. And iterations, ITERATIONS, iterations is total we have 5,000 iterations, okay. Then after this, we have n is equal to length of x. So here we will take length of x. You will understand why. We have to take this, what is the array's length. And now we'll have a range for I in range of. So how many iterations you want? Okay. So you as I previously told you that using the low learning ratio will actually make you give high number of steps, okay, iteration, high number of iterations. I told you that, okay. So where is that? Let me check. Mm, Low value of learning rate will help you, okay. So learning rate helps us decide the right amount of jump from the previous slope to the next slope such that minima is reached. A large value of learning rate may result in missing the minima, whereas the very small value of learning rate may lead to increase in the number of steps, okay. So this will lead to increase in number of steps. So I'm passing, since our learning rate is 0.01, I'm passing 5,000, okay. Let's check. That is number of range of 5,000. Instead of 5,000, I have already given iterations. So I will pass iterations variable here. So you know that the y predicted is m into x plus c. What is this? This is the equation of our line. Okay. This is the y predicted is mx plus c. And what is our cost function? Cost function comes out to be. So first we have to take sum of square, right? So what is our cost function? It is y minus y predicted whole square. So we will take it like for val in y minus y predicted. So we have y minus y predicted. So we get this, right? After doing y minus y predicted, we'll get this. And then you have to square it, okay? And then you have to square it. For that thing, you have to pass, well, whatever value you get, you have to value into 2 square, value power 2. You will get y minus y predicted value of squares, okay? So now, whatever value you get, you have to do the sum part. Sum of list. So you'll get list of values from this. So you'll get list of values from this. You have to add all the values, right? So sum of this. And then after that, you have to pass. So we have got the cost function, right? So you have got your cost function, which is a sum of square roots today. Now you have to pass W next and B value, which is our slope. Slope and DM is our differentiation of slope. We have to find the differential of slope. So what is that value? Let me check. That comes out to be minus 2x into y minus y cap. Okay. That comes out to be minus 2 into x of y minus y cap. So into, so I have to sum of, so before doing sum, y minus y cap, let me do y minus y predicted. So I will take this as list control C and control V. So I want only y minus y predicted, right? So value for value. So we got y minus y predicted value and we have to multiply with that value x. Okay. But this is not a, we don't need a list, right? Do we need a list? Do we need a list? That's what we have to ask. We are not doing performing some operation. Do we need a list? No, we don't need a list. So we have to just do minus 2x into y minus y cap. So minus 2 into x. What is x? We have to pass it x like that, but we have to do the summation as well. Sum of x into y minus y predicted. Will it give? Let's check. Y minus prime predicted is this. And when I have done to x multiply of x into y minus y predicted, I have done the summation. Okay. We have the summation part as well. Summation we have done. Have we done? Okay. So next we'll perform similarly for DC. That is a constant value. This also comes out to be minus 2 into sum of, so this is just y minus y predicted. So we have computed our DC as well. So differentiates with respect to the constant, and we have done this differentiate with respect to the slope. So for easy computation, we have to divide this cost function dm and dc by length of the array. So which comes out to be, so 1 by n into this, and minus 2 by n into this sum, and minus 2 by n into sum. Okay. So you have got dm, dc, and da cost function as well. Okay. So now, so what we have to compute? So now we have to compute m, right? M is m minus learning rate into dm, whereas c is c minus learning rate into dc. So let's see for each iteration, we print slope equals comma intercept equals comma iterations comma cost. We are using format, and we'll pass value of m, that is slope, c, that is intercept, number of iterations is I, and what is our cost? That is cost is c was. Okay, so let's run this. So invalid syntax. Okay, so this should do bad. Let's run this. Okay, now let's pass. So let's run this. Now let's pass gradient descent. Descent gradient descent value of x and y. So x comma y. Yeah, you could see now. So in the first iteration, our cost function comes out to be 22.4. It is huge. I mean, it should be close to zero. Okay. Our slope comes out to be 1.3 and intercept is 1.088. Okay. In the zeroth iteration. Okay. Which we have given default value of m and c. So after one iteration, the m and c, the slope and c gets changed, and then in the next iteration we have 1.54 and in this should be zero first. This is the first iteration. Zeroth iteration is our first iteration. In the next iteration, so let me change from one iteration. Okay. Okay, so this is our first iteration. Okay, we got in first iteration 22.4 as a cost function, and the slope and 1.3, and the intercept is 1.08. As in the second iteration and the further iterations, you can see the slope got decreased. The cost function got decreased, which means the error is decreasing. Okay. So 22, 13, 8, and 5, 3, 2, 1, it's decreasing. Okay. You have to see the point where it start increasing. Okay. Once again. So if I have to explain from this graph, so you see the cost function is increasing until here it reaches minima, and from here it will once again get increased. Okay. So you have to find this minima point where it starts increasing again. I mean, now it's decreasing, right? Wherever it start increasing, you have to find. So it's decreasing 0.69, 0.68, 0.67, 0.63. So let's go down 0.62, 0.62, 0.62, 0.62. Okay, so 0.61, 0.62. Okay, here, somewhere over here, you could see that 0.62 is here, 0.62, 0.6. One is it reached 0.61. Yeah, 0.619. Okay. Here you can see that 0.62, 0.619, once again 0.62. So this is the minimum point. Okay. This is the minimum cost function it is reached. So, so the minimum cost function has reached over here, which is 0.61. That is error is 0.619. And then once again it's increasing. It's 0.62 to 0.62. Once again it's increasing. From here till here, it's once again increasing and going. So this is how the gradient descent works. So I hope you understood. So this is all about the gradient descent part. Let's move to the next concept now. So the next concept is, after this is evaluation matrix. Okay. So I hope this is also evaluation matrix. Okay, evaluation matrix, and yeah, evaluation matrix. Evaluation matrix. Where is it? Evaluation matrix. Okay. So for each model, there are different parameters used to evaluate the performance of the model. In case of linear regression model, some of the parameters of evaluation are mean absolute error, mean square error, and root mean squared error. So mean absolute error. So the mean absolute error of the actual response values from the predicted response values. That is, if you want to understand mean absolute error, you just say mean one bar absolute error. First you calculate absolute error, and then you will apply mean. Sum of the mean absolute error. So mean of the absolute error. That is y minus y cap absolute value will take, and then you will apply mean. Mean squared error is, error is y minus y cap, square it, y minus y cap whole square, and then you will take the mean 1 by n. Immediately root mean squared error is root of the squared mean error. Mean square. Okay. This is all about the mean absolute error, mean squared error, and root mean squared error. So let me do the definition first. The mean of the absolute error of the actual response values from the predicted response values. Okay. The mean squared error takes the mean of the squared deviation of the values. Okay. Root mean square error takes the square root of mean squared error. So mean absolute error value remains the same no matter whether the original value error values are the same or highly varying. Root mean square error, on the other hand, seems to be highly sensitive to the variation in the error values. The conclusion we will do, so parameters to decide which evaluation parameters to use. Interpretability, we use mean absolute error, then we root mean squared error, and then it mean squared error. So which is sensitive to extreme variation, that is, which is sensitive to outliers, mean square error is more sensitive, and then root mean squared error, and mean absolute error is the least sensitive one to the outliers. So let me teach you that concept over here as well. So we have seen this concept root mean squared error and all means absolute error. So let's come to the concept from here. Okay. So evaluation metrics. Okay. How much error regression. So mean absolute error, mean of the absolute value of the error. You have to understand mean absolute error is the mean of the absolute value of the error. The mean squared error, you read it as mean of the square of the errors. And root mean square error is root square root of mean of the squared error. There is also another error called mean absolute percentage error. Percentage, you know, right? Y minus actual minus predicted by actual into 100. So we have to take the mean of that. So 1 by n. So let's say you have an example where error comes out to be 2. Okay. Absolute error will be 4. So these are the total data samples. We have 10 data samples. The sample size is 10. 3, 6, 9, 10. Okay. So error comes out to be 2. What is the absolute error? 2. What is the squared error? That is 4. When you apply for here, the error comes out to be 1, 1, 1, 1 and 3, 3, 3, 3. So absolute value will be same and the squared will be square of the each numbers. Okay. So now let's see this error. Okay. The error is 0, 0, 0 and the only one outlier is present where 20 error is 20. So what is the absolute value? 20. And what is the squared value? 400. So now when you try to compute all the three metrics, evaluation metrics parameters, you will see that over here, when you take the mean absolute error, you will sum all this 4 plus 4 plus 4 and divide by 10. Okay. So we'll get 4 plus 4 10 times, that is 40 by 10, that is 4. Okay. That is the mean square error you'll get. When you take the absolute error, you'll get 2 plus 2 divided by 10, 20 divided by 10. We get the mean absolute error to be 2. And the root mean square error is nothing but square root of mean square error, which is root 4, that is 2. Similarly, when you compute over here, you will get 1 plus 1 plus 1 plus 1, 1 plus 1 plus 1. So plus 3, 3, 3, 3, 3, 6, 9, 12, 15 plus 5, 20. 20 divided by 10, you will get mean absolute error is 2. But your mean square error comes out to be 9 5 is 45 plus 5 50. 50 root 50 comes out to be root mean square error through 50. 50 divided by 10, 5. Mean of square error is 5, whereas root 5 is comes out to be 2.3, which is our root mean square error. Okay. And now in this example, if you see here also mean absolute error comes out to be 2. And root mean square error comes out to be 6.3 and mean square error is comes out to be 40 because of this. Okay, 400 divided by 10, 40. And for root 40 is 6.3. So what we have seen that in all the three cases, the mean absolute error remains constant for various error values. Okay. So for interpretability, we use mean absolute error, and then we will use root mean square error, and then we will use mean square error. So which are sensitive to outliers? You can see this 400 is an outlier here. So the root mean square error is sensitive, but mean absolute error is not at all sensitive. Mean square error is sensitive to outliers, then root mean square error is sensitive, then mean absolute. Okay, this is all about the evaluation metrics. So now let's move to the concept of R square and adjusted R square. Now let's look at the concept called R square and adjusted R square. So R square is a coefficient of determination. So let's see the theoretical part. And so difference between R square and adjusted R square. In case of adjusted R square, we include only the important and useful variables. Okay. Whereas in R square, all the variables are included. So in this tells us, so let's say we have in some independent variables, let's say 5 independent variables and 1 dependent variable we have. So if all the 5 independent variables have equally actually have that equal strength of affecting the equally or unequally, they have some kind of affection on the output, then we will say that all the 5 variables are important. And if let's say if some of the variables are not so important, then we will actually remove these variables so that that doesn't have negative effect on our output. Okay, so this is once again, let me say, in case of adjusted R square, we include only important and useful independent variables, whereas in R square, all the variables are included. Mathematically, R square is calculated by dividing the sum of squares residuals, okay, by the total sum of squares and then subtracting it from 1. That is, R square is calculated by sum of square residuals by the sum of square totals and subtracting it by 1. In case of SS total, that is sum of square total measure total variation. Okay, this sum of square total measures total variation. SSS measures sum of square residual measures explained variation, and sum of square regularization measures unexplained variation. That is, R square is explained variance by total variance, or 1 minus unexplained variance by total variance. But that is 1 minus sum of square residuals by sum of square total. So sum of square residuals plus sum of square regular is equal to sum of square total. So R square is explained variation by total variation. So you have to understand this. Sum of the R square is 1 minus sum of square residual by sum of square total, or it is sum of square regular by sum of square total. The family, if you want to write, this will become sum of square, that is y minus y cap d whole square by y minus y total. Sum of square total residual by sum of square total. So R squared is also called coefficient of determination. It lies between 0 and 100%. 100% is R squared value of 100% means the model explained all the variation of the target variable, and the value of 0% means zero predictive power of the model. Okay. So R square should be higher as possible, because higher the value, it tells that the target variable means the variation in the target variables is explained by the independent variables or not. Okay. The predictive power of the model is explained based on the R square. Higher R square, better the model. This is about R square. So let's come to the adjusted R square. So it measures the proportion of variation explained by only those independent variables that really help in explaining the dependent variable. We're not considering those independent variables which doesn't have any effect on the dependent variable or negative effect on the dependent variable, but we are only considering those independent variables that really help in explaining the dependent variable. It penalizes you for adding independent variables that do not help in predicting the dependent variable. So it will penalize, like let's say, take this example. So you have taken one variable, okay, R squared. So I also want to say R squared will always keep on increasing. It won't decrease. Whereas adjusted R square will decrease if there is an independent variable that has no effect on the dependent variable. Okay. So you could see when we have one variable, we have R squared 67.5% and R squared adjusted R squared 67.1%. And when you had two variables, you could see R square increase, but adjusted R square also increased fine. When we have three variables, you could see R square increase, but adjusted R square has decreased. So we have negative impact on adjusted R square. So we have to take out the third variable. But you understand R square is always adjusted R square is always less than or equal to R square. Okay. And also R squared will never decrease. It will always increase in your own applying variables, whereas adjusted R square will decrease if no, there is an independent variable that do not help in predicting the dependent variable. Okay. So adjusted R square can be calculated mathematically in terms of sum of squares. The only difference between R squared and adjusted R square equation is degrees of freedom. In the above equation, degrees of DFT is the degree of freedom, n minus 1 of the estimate of the population. You know that n minus 1, the degrees of freedom total is n minus 1, where n is the population estimation, variation or variance of the dependent variable, and DFT is the degrees of freedom, n minus p minus 1 of the estimate of the underlying population error variance. This is the underlying population error variance, okay, n minus p minus 1. Adjusted R square value can be calculated based on value of R squared, number of independent variables predictors, okay, total sample size. So adjusted values can be calculated by R square, that is 1 minus R square. R square we have number of independent variables, that is N is P is number of predictors, that is independent variables, that is P, and total sample size, that is N is total sample size. So total sample 1 minus R square into total sample size minus 1 by total sample size minus number of independent variables minus 1. So these are the values. This is how adjusted R square can be calculated mathematically. So every time you add an independent variable to a model, the R squared increases even if the independent variable is insignificant. Okay, and always R square increases whenever you add an independent variable, even if the independent variable is not significant. It never declines. Whereas adjusted R square increases only when independent variable is significant and affects the dependent variable. Okay. In the table below, adjusted R square is maximum when we include two variables. You could see adjusted R square is 84% when you have two variables. It declines when the third variable is added. So 84% is decreased to 81.7%. Whereas R square increases when we include the third variable as well. So it has increased by 3%. It means the third variable is insignificant to model because our adjusted R square is what we see if the variable is significant. True adjusted R square can be negative when R squared is close to zero. So when R square is close to zero, let's say R square is zero. As I said, our adjusted R square is always less than or equal to R square. So it can be less than zero, that is negative, if R square is zero. So adjusted R square values always be less than or equal to R square, that is. So which is better? Adjusted R square should be used to compare models with different number of independent variables. This you need to keep note because we know that it will be able to find out the insignificant independent variables that are present. Adjusted R square should be used for while selecting important predictor independent variables for regression model. So this is all about R square and adjusted R square. So if you want to find the adjusted R square, you just have to apply this formula. So 1 minus R square we have find out from this formula, R square formula we have. What is the formula of R square? That is summation of I minus I. This is summation of square residual by summation of square total. So the summation of square residual and summation square total we have done. And then we have n minus 1, that is sample size. N is whatever the value of n, y dot shape of 0. This gives the sample size. And number of predictors, P is going to give number of predictors. Okay, fine. And the sample size, right? P is number of predictors. Let's check that. And is total sample size, number of predictors. So this is all about adjusted R square and R square. So now let's move to the next concept. So multicollinearity and how to treat it. Okay. So the concept of multicollinearity we will check now. So I will be completing the coding part for this linear regression in the next video, that is part 2. So this was all about theoretical concepts you need to understand for doing linear regression problems. So watch the next video for the linear regression coding concepts, okay? How to code using linear regression algorithm. So now let's discuss multicollinearity. In real life, when many independent variables are involved in the model create to help predict the output variable, there may be a chance that any two independent variables are correlated. This is called multicollinearity. For example, in housing price model, if say carpet area is high, this also implies that there would be more number of rooms. So these two independent variables implies each other, okay? And hence, this may influence on the resultant model. Models are always built on the assumptions that all the predictor variables, that is independent variables, are not related to each other. Okay. If this assumption is not true, it results in less reliable model. Hence, it is important that it should not be it should be no multicollinearity. How to detect multicollinearity? Visualization using heat map. Okay. So in the coding part, I will going to teach you when I do the coding part how to draw heat map and check if there is multicollinearity using statistical measure, that is use correlation matrix. So another statistical measure is variance inflation factor. So variance inflation factor tells us how much the variance in the regression coefficient increase if the predictor variables are detected. Okay, it is given by formula where f is equal to 1 by 1 minus r squared. In a way, it depicts the extent of multicollinearity. A value of 5 or above indicates high multicollinearity. So variance by inflation factor of 5 or above indicates there is a high multicollinearity. Okay. So what are the ways to prevent multicollinearity? So drop one of the way related dependencies to eliminate the problem of multicollinearity. So feature engineering. So design the features in a way that related variables do not harm the model. So, example, carpet area and the number of rooms are kind of related independent variables. A ratio can be taken as a new feature to kind of model the depicts area per module, area per room, carpet area by number of rooms. Okay. So now let's see this in this what is multicollinearity part. So multicollinearity occurs when your model includes multiple factors that are correlated not just to a response variable but to each other. In other words, it results when you have factors that are bit redundant. You can think about in terms of cricket game. If one player catches the ball, it's easy to give credit. If three players are going for the catch simultaneously, it's much more difficult to determine which of the three makes the biggest contribution to the catch. What does it mean? Multicollinearity increases the standard errors of the coefficient. Increased standard errors in turns means that coefficient for from independent variables may not be found significant different from zero. In other words, overinflating the standard errors, multicollinearity makes some variables statistically insignificant when they should be significant. With more multicollinearity, those coefficients must be significant. So just understand this. So if your independent variables are related to each other, instead being related with the dependent variable as well, then there is a multicollinearity. You should take care of this multicollinearity by doing feature engineering or just being one of the variables. If multiplication is a problem in your model, the VAF variance inflation factor for a factor is near or above 5, the solution may be relatively simple. Try one of these. Remove highly correlated predictors from the model. If you have two or more factors with high VAF, remove one of the model because they simply redundant in the information. That is repetition, right? So you have two repetition in your column, so this will affect your model. Okay, the model performance will be getting reduced. So remove one of the correlated factors usually doesn't drastically reduce the risk. Consider using stepwise regression or specialized knowledge of the data set to remove this variable. Select the model that has highest R squared value. Also check the adjustment R squared. Okay? So using that, so while performing which variable to take among the independent variables that are correlated to each other, select the one that is having higher R squared or also check the additional R squared as well. Use the principal component analysis that cut the number of predictors of the set of correlated components. Okay. So this is the code for calculating the variance inflection factor. Okay. So I will teach you in the coding part these things. Let's see the notes that I have prepared. So multiple collinearity and how it to treat it. What happens if one independent variable is highly correlated with one or more independent variables? Then it comes multicollinearity. These two independent variables are related to each other. So number of bedrooms is independent to number of bathrooms. So if there are number of 5 bedrooms, then there will be a possibility that there are 5 bathrooms as well. So these are correlated, right? So this is how correlation matrix looks. Okay, so I will draw it in a heat map and represent the correlation matrix in a heat map. So the variance inflection factor is 1 by 1 minus r square. Variance inflection factor is 1 and infinity. Value lies between 1 and infinity. And if a value is above 5, thumb rule is value is above 5, you have then the independent variables are related to each other. VF tells you how much the variance of an estimated regression coefficient increased if your predictors are correlated. So this is a okay. So let me show you that once again. So in a way, it depicts the extent of multiplicity. A value of 5 or above indicates that there is high multiplicity. So how to prevent multiplicity? Drop one of the variable and do feature engineering like y is proportional to x1 comma x2. Then do y is log, I mean, take log x1 so that it doesn't have same effect. Okay, y is proportional to log x1 comma x2. So weight and height are related as weight increase in height leads to increase in weight as well. So combine this for getting the body mass index like that. Okay, so from this, I have completed all the concepts that are needed to be known in regression. So in the next video, I will be doing the linear regression coding part where we will take advertising CSV file and we will perform some of the linear regression model on that. And let's apply ordinary least square algorithm and check the and also we'll apply statistics model oriented square and also the machine learning linear regression model as well. And we will find out the best fit line for the data samples that we have taken. And we will see what is the slope and intercept, and we will also calculate adjusted R square as well as mean absolute error, mean squared error, and mean squared error as well. So thank you for attending the session.